transparent to the application. So the application does not know necessarily that its connection has been offloaded, although it can find out. If you look back at the at the options that I dumped out, so we actually have a chimney offload state in here where you can disable chimney offload on a global basis. When you dump out, if you use netstat to dump connections, you can see for each connection whether or not it's offloaded by just using the netstat option. And then the other thing is that because we took this sort of stacked approach, we can plug in other layers. So for instance, if you have a TCP connection that's secured using IPsec, we are in the process of actually speccing out support for offloading IPsec state to a piece of hardware as well. So you can start taking the IPsec processing for a connection and offload that completely so that you're still only dealing with request level operations, send, receives, and so forth. The final piece is that the area where we continuously innovate is we're always monitoring what connections are doing and picking good candidates for moving off the operating system. The results that we get from this are actually pretty dramatic. Now, the number that I have here is actually already outdated. We were seeing 50% reductions in CPU utilization just with gigabit. At WinHEC, we demonstrated with one of our partners actually filling a 10 gigabit Ethernet connection to capacity, essentially. We're doing about 9.3 gigabits at 32% CPU utilization. And that was just with their current generation of hardware. So the way that things are starting to develop is that we have vendors who are building offload capabilities into essentially every single motherboard for like a $5 price delta. So this is something that we anticipate having everywhere. Not only having everywhere, but also having features like IPsec support everywhere so that we can start just assuming that you can use socket options or whatever to secure connectivity using protocols like IPsec. So that's enough for bandwidth scalability. Another dimension of scaling up the networking stack's behavior is looking at what happens when you have really long paths. So you're talking from here to Zurich, or from Australia to Tokyo, or you have paths that go around the world, for instance. This has been pretty challenging for TCP, and one of the big reasons is just the sheer amount of data that you're dealing with. So if you have a gigabit at 500 milliseconds, which is admittedly a pretty long path, but just to make the point, the buffer sizes at both ends would be about 64 megabytes, and you'd have 32,000 packets in flight. Going down to 100 gigabit at the same latency, now you're up to about 3 million packets. And what happens as you have so many packets in flight is that whatever your loss rate, however low your loss rate happens to be, the probability that you'll lose a packet becomes higher and higher. And the moment you lose a packet at this kind of scale, ramping back up into the window that you had before takes longer and longer. What does that mean? So that's where we come into congestion control. So congestion control is how the TCP sender tries to avoid flooding the network. The basic idea behind it is that we try to ramp slowly into the capacity of the network, and when we get a loss, we figure that we've probably oversubscribed the network and we should back off. So that's the basic idea behind classic TCP congestion control. The problem with that is that you have to actually lose a packet in order to sense the capacity of the network. And there are alternative schemes. There are schemes that are based on sensing delay, for instance, where you keep introducing packets to the network, but then you also try and measure whether the delay in the network is increasing or not. Because if the delay is increasing, it's a sign that the network might be starting to buffer packets, and maybe you should scale back the rate at which you're introducing those packets. So delay-based schemes have been around for a while, and they have the benefit that they ramp up pretty quickly, but the downside is that when you run them side by side with the classic TCP, they just go in and suck up all the available bandwidth, and the classic TCP congestion algorithm suffers. And clearly this isn't something you can deploy on a broad scale, without addressing that issue. The way that we addressed it in Windows Vista is with an algorithm called compound TCP that came out of MSR Asia, and that's being validated by a number of research centers, including the Stanford Linear Accelerator folks. So the basic idea behind this is you start out with a loss window, which is what you would have with classic TCP, basically a window based on whether you've sensed any losses or not. But then you add on that a window based on whether you've sensed delay in inside of the network. So if you've not sensed any delay, that's a sign that you can introduce a little bit more to the network. What that allows you to do is it allows you to take the ramp up that you would have with a loss-based scheme and augment that with the ramp up that you would have with a delay-based scheme without penalizing any classic TCP flows that are sharing the network path with you. So results on that. So the basic idea again is you want to avoid losses and recover quickly when someone else causes a loss, but you also want to be fair to connections using loss-based congestion control. And again, that's something that actually pays off way more than you'd have any right to expect. So we see in the scenario that I described earlier where our Microsoft.com folks were testing between Tukwila and the Bay Area, I mentioned that they got a 40x improvement right out of the gate. When they turned on the compound TCP algorithm, they got another 2x improvement. So they got another 50% reduction in the transfer time because they were spending less time waiting to figure out what the capacity of the network was. So that's basically a cross-section of some of the things that we've done in the Windows networking stack. Often I'll actually show a slide with a full scale of the features that we've implemented and the security features as well, things like secure sockets, the IPsec capabilities, the advanced firewall, and on down the list. And the problem is that there's never enough time to talk about everything that's changed. So what this is intended to do is to give you an idea for the scale of the change that we've made and how long we've spent validating the change, how much work has gone into building a platform that can evolve and that can continue to become more and more secure over time, even after we've released it. And what we ask from you is basically help in building on this foundation and taking it forward. That's a combination of things. First of all, ensuring that the tools and products you have really do light up. If there are things that we've done in the networking stack that, for instance, would impede the tools that you have out there, let us know. If there are additional features that you think would be cool to incorporate, let us know about those as well. The second part of that is to actually innovate on top of some of the capabilities that we've built. In particular, the Windows filtering platform allows you to do some very cool things. I didn't talk so much about features like secure sockets that actually allow you to use socket options to negotiate security between two machines using IPsec. Further on down the line, we introduced support for kernel mode IP helper API. So if you write drivers in kernel mode, whatever stuff that you could do in user mode using the IP helper API in terms of enumerating addresses and so forth, you can do that a lot more simply in kernel mode now. We have support for kernel mode sockets as well. So if you're writing the applications in kernel mode that use the network, we have a sockets-like API that you can use to do that much more easily. So there's no shortage of new things, no shortage of innovations that we've done, all within the scope of the kind of thinking that John talked about in the earlier talk on SWI. If you have feedback for us, here are some places you can send it. We also have content that's already out there and that's building, we're adding to on an ongoing basis that you can take a look at to find out more. I will be in the booth afterwards answering questions. I'll also take questions right now. We have a talk on the Wi-Fi stack, which is also completely new in Windows Vista and which builds on a lot of the capabilities I've talked about here. And then Adrian will be talking about the heap and what we've done there. And then finally, going all the way up, almost all the way up the stack to Internet Explorer 7, the things that they've done and how that takes the work that we've done in the networking stack and in this Secure Windows initiative even further. So with that, questions? Yeah. Yeah. So I think the question is, if firewall vendors assume particular port ranges, how does that play with the fact that we allow the dynamic port range to move around? So the answer there is two things. First of all, if you're a firewall vendor, then you can actually lock down these capabilities. moving the dynamic port range is a capability that you can block essentially using group policy in a particular enterprise. Now, were you asking really about port randomization, maybe? I see. So the way that the firewall platform, the filtering platform addresses that is that you actually associate the policy with the application itself. Well, if you have a specific application in mind or a specific user in mind, you can author policy that refers either to the ports or to the operations that you want to allow or to the application process itself, for instance, defined by the executable name, or to the user. So what we've done is we've tried to give you a range of options for how you take that policy and actually specify how it should be applied. Does that answer your question? If it doesn't, then I can try and understand the point you're making in more detail at the booth. Yeah. Come again? Those policies? So the Windows filtering platform actually has a filtering database to which you can deploy filters from a central location. So for instance, I don't know if you've seen the advanced firewall user interface in Windows Vista, but that's something that either an end user or an administrator for a network can actually use to author policies and roll them out to various organizational units, various desktops, and have them take effect there. Well, once you've authored the policy, the filtering platform picks it up, so the application doesn't need to be involved. Mm-hmm. Come again? Oh yeah, an application itself can be authored to provide its own policy as well, in addition to the administrative policy. And the filtering engine is responsible for doing the arbitration around if there's a conflict, who wins. So and we have a set of rules for doing that arbitration. Yeah. And the way that we've handled that, we've done it at multiple levels. So for instance, if the firewall is accustomed to dealing with port numbers, now we allow you to actually deal with operations. So if you care about listens, about accepts, about connects, regardless of the port that's being assigned to them, we can allow you to actually say, for instance, the following application cannot connect. Or the following app. So in other words, rather than dealing at the low levels, kind of like after the fact details, after the port has been assigned or whatever, you just plug into the state machine that we provide. When we're about to assign a port, we will call out to you and say, we're about to assign the following port. You don't even have to know what the dynamic range is, because if you're plugged in, whatever the port is that we're about to assign will tell you.
Okay, so in essence, it becomes irrelevant.
Exactly, that's what I'm getting at.